Evan, the calc teacher! Yay! Okay, so I've kind of figured out that you guys can hear my breathing over these, which is a little bit creepy. Hopefully that doesn't put you off too much, but got me thinking that maybe I would do an ASMR lecture. So I've got to figure out where the microphone is. I think that's where it is. And I'll speak whispers into it. Hello. Today we are covering integration by substitution. And, well, I don't really know if speaking like this the whole time is going to make me a very good instructor, so I think I'm going to stop. Yeah, that was pretty weird, wasn't it? Anyway, substitution. This is basically the chain rule in reverse. And so you might wonder why we're starting out with the chain rule instead of maybe the product rule or the quotient rule. And actually there is no quotient rule in reverse. You'll remember that the quotient rule was a special example of the chain rule plus the product rule. And the product rule plus chain rule. And so all we have to do is get the chain rule in reverse, the product rule in reverse, then we get the quotient rule in reverse for free, but it's not really a thing. We'll cover the product rule in reverse in the distant future. It's like after your next exam, so don't worry about that anytime soon. But this one's pretty helpful. This integration by substitution is good. So we're going to be thinking about the chain rule in reverse. So let's just recall the chain rule. Call the chain rule. What's going on here? We have d dx of f of g of x. And that gave us f prime of g of x times g prime of x. Or you'll remember it from the way I like to say it, derivative outside, keep the inside the same, multiply by derivative of the inside. So really, what we're looking for here we're looking for integrals of the form integral f prime of g of x times g prime of x dx. And really we have, this, everybody's now going to say this is just f of g of x because it's the opposite of the above, right? These two lines say the same thing. But we have a nice notion of how to write this out in an integral way so that maybe it makes a little bit more sense, or maybe you can see what g prime and f prime should be a bit quicker. So what do? We just like with the chain rule, we have an inside and the outside. Just like with the chain rule, we have an inside and an outside. But in this case, we actually label them as new pieces. In this case, we label the inside I spelled that wrong. I did spell label wrong. That's fine. We label the quote inside as U most often. And that's why this integration by substitution is most often called, you'll hear it called U-substitution. So basically what we're doing when I have this line up here, call this asterisk. So in asterisk, we let g of x equal u, so then g prime of x dx we call du. And why do we call it like that? Well, it turns out you can kind of start to see this. I could rearrange this. You get exactly that g prime of x equals du dx, which, what is that? This is just d dx of u, and we had just called u g of x, so this is just d dx of g of x. So that's why, that's why we use this form, but really we want to think about it like this. G of x equals u, and g prime of x equals du, because what happens in asterisk, right, I'm just going to keep that, trying to get that on the screen there. In asterisk, if we replace g of x with u and g prime of x dx with du, then what are we really writing down? We write integral f prime g of x g prime x dx. If we replace them with what we've called them in this squared portion here, I can rewrite this down. This is f of u du. F prime of u du. And all of a sudden, when it's written as f prime of u du, it makes perfect sense that this is just going to be f of u plus c. And so if that piece is f of u plus c, really what's going on the whole time, u was just g of x. And so this is really f of g of x plus c, which is exactly what our chain rule was saying. So this is the same as what the chain rule said. So then a lot of you are saying, why can't we just leave it like the top one there, this asterisk? You could, if you were really good and great at recognizing things, you totally can. But U-substitution kind of forces you to be able to find things the way that you would want to find things when a chain rule might be involved. So I'll give you an easy example and a hard example, and I'll show you why the U prime is maybe or looking at U is maybe the right way to do this. So this is an easy example. And in this easy example, it won't be quite clear why we want to use a U substitution, but in the hard example, it's going to be very clear. So the easy example, let's just look at the integral of x squared plus 3 to the 4th times 2x dx. And in this form, things are starting to look very clear because we basically have an outside and an inside, and then we should be able to figure out where things go from there. But let's try to work this through with the U way and see if that makes our lives easier. So let's see if we can find an inside and an outside. As always with these, the inside is going to look like whatever is inside parentheses if nothing terribly complicated is showing up. So inside, just like with the chain rule, inside is akin to the piece in parentheses inside the parentheses. So in this case, the inside, we want to label the inside as U, also known as gx equals U. So we'll call the inside U equals, we're going to call that the piece in the parentheses, and you guys look at the integral above and we see that the piece in the parentheses is x squared plus 3. And we can never work with only U. We always have to work with both U. Here, I'm looking at the top here. We have to work with both U and we have to work with du. And du just means we take a derivative of U. This is very similar to implicit differentiation, right? Really, that is what we're doing. We're doing implicit differentiation here. And we get 2x dx. And so I hope I hope 2x dx is in the integral. And surprise, surprise, it is. So that means we're good to go. That means that this sort of U substitution was what we wanted it to be. So all we do is we plug these numbers, this x squared plus 3, we substitute that in for U, and we substitute 2x dx for du. So basically we're working backwards on these last two equations. If I rewrite out my integral, then I can think about this U is just that, and this du is that, right? In some case, in some sense, I'm split right there. I have a u to the fourth power, and then I'm left with du. And then the world makes complete sense, because do we know how to integrate u to the fourth? Yes, we do. It's u to the fourth plus 1 divided by 4 plus 1, also known as u to the fifth divided by 5 plus c. And preferably, my answer will be in the form of x and not in the form of u. So I'm going to take this one step further and replace, right? This u was x squared plus 3 there, but this u over here is still x squared plus 3. And now it's to the fifth power divided by 5. So the fact that u was x squared plus 3 on the left means that u is still x squared plus 3 on the right. And so we can substitute it back in terms of x at the end. Now, when I say this was the easy example, this might not seem particularly easy upon the first try, but if we kind of look back at the original integral and we see what's going on, you know, some of you might be able to instantly recognize this as some sort of f prime of x gx situation going on, where f prime is something to the fourth power. And so if f prime of x g prime, f prime of g of x times g prime of x, if that equals f of g of x, then basically you're saying you keep whatever's on the inside the same, you keep the x squared plus 3 the same, which we got in our answer, and you just take the derivative of that outside. The tough part here is, like, it's tough to recognize what the outside actually is. The outside could be to the fourth power, it could be 2 times to the fourth power, it could be the x even on the outside, and blah, blah, blah. So you really need to go through the U substitution process. It kind of helps you figure out what the outside should actually look like. It sometimes is going to look like more than just your power, and other times it won't. So that's really why we use U substitution. And so this was the easy example. I'm going to show the hard example now. And yeah, they can get a little bit tricky a little bit quickly. So we'll do we'll do this example. So in this example, we have the integral of x squared times x cubed plus 1 to the 2/3 power dx. So when I look at this, thankfully I still see parentheses, and that should help me out on what I should call u and what I should not call u. So I see the parentheses and I say, okay, I probably have an inside. Let's call the inside u once again. And so u we're going to call the inside, which is x cubed plus 1. I can take that right away. And then we need to calculate du. Like, you can never get away with only u. You always need to find du as well. And in this case, du is going to be 3x squared dx. Once again, it's just implicit differentiation on u. So this is tricky now. We have to find, this is an absolute need to find this inside of our integral. There's no way around it. You need to find 3x squared dx inside of our integral. And I see an x squared dx inside the integral. So I see an x squared dx in the integral. Right? There's no reason that I can't rearrange my two pieces. There's no reason I can't move the x squared that's sitting on the left. I can't move that over by the dx. So I certainly do see an x squared dx in the integral, but the 3, I'm missing a 3, and that's really strange. But I'm missing a 3. And that's a little tough. So what we like to do in math whenever we're missing something, this is something that you catch on to if you're sitting in math for 8 years like I have been, is that you force it in there. And okay, you can never put it inside by itself and hope that everything works out, because there's no reason that 1 is equal to 2, because there's no way I can do it. But 1 is equal to 2 minus 1, right? So if I can always like add or subtract or multiply or divide by things, as long as I'm not really changing what the expression is saying as a whole, then I'm safe to do things. So what I want to do is write my x squared dx as 1/3 3x squared dx. And hopefully everyone sees that 1/3 times 3 has done nothing to my problem, but all of a sudden du has shown up. So this is really 1/3 du, as well as being x squared dx. And this is the way that sometimes I like to teach it, but a lot of other people have a much more clever way of teaching it. And that is that they see their du here, and they see that they have x squared dx. I'm going to pull this down. We have this du equals 3x squared dx, and we also have x squared dx shows up in the integral. So what do people do is they just take this expression and that expression, and they notice that if I divide by both sides by 3, if I divide my du expression by 3, then I get du over 3 equals x squared dx, which is, of course, what's in the integral. So whichever way you want to think about it, basically we have to end up with this sort of idea, this 1/3 du, or this du over 3, whatever you want to think about, you end up with that 1/3 du, and that's actually what you're going to use when we substitute our integral. So I'm going to rewrite my integral down here. X squared times parentheses x cubed plus 1 to the 2/3 dx. I rewrite this as x cubed plus 1 to the 2/3, and then x squared dx. And however we want to think about this piece is u, and this piece is not actually du, it's 1/3 du, or we can think about it as du over 3, however you want to think about that. That piece is now 1/3 du. It's not quite du, but we can get away with writing 1/3 du. So we do. And we write it like this. We write u to the 2/3 times 1/3 du, and that can get rearranged to 1/3 integral u to the 2/3 du. Now our life gets easier. We know how to integrate this with the power rule. We integrate this with the power rule just as we've been doing for the last 3 days. It'll be 2/3 plus 1 divided by 2/3 plus 1. And 2/3 plus 1 is actually, it's 5/3. 5/3 is the same as multiplying. Dividing by 5/3 is the same as multiplying by 3/5. And so 3/5 times 1/3 is actually 1/5 u to the 5/3 plus c. And we can always, and I will ask for this on exams, we always want to substitute back in terms of x. So when we substitute back in terms of x, we just recall that u was, we see it right here, and we see it at the top. What was u? It was x cubed plus 1. Now it's to the 5/3 plus c. So that's the slightly trickier version, right? Because we had to come up with this 1/3 factor that wasn't in our original problem. And that's where all of the cleverness comes in these substitution problems, is how can I force du to show up? We're really working really hard to force du to show up. And u is almost always going to be the piece in parentheses, but we really want to force du to show up as well. So there are a couple cases of this, external cases of this, both with the exponential function, the log function, that I want to cover. So let's cover this in exponential and log function versions. So we'll remember that, recall the chain rule for e to the f of x and the natural log of the absolute value of f of x. What do these look like? d dx e to the f of x is f prime of x e to the f of x, and d dx of the natural log of the absolute value of f of x is f prime of x divided by f of x. So that means that if we're doing the chain rules, how do we want to interpret things if we're working with chain rules? Really, how do we find our insides? So in both of these cases, we're looking at the right-hand side. So if we're looking over here, our quote-unquote inside is either the piece in the power, it's the piece in the exponent, right? It's the piece in the exponent, or it's the denominator. So this starts to kind of force you to broaden your horizons as to, can I really find the inside correctly? Or can I really find U correctly if I'm working with U-substitution? We're kind of forced to broaden our horizons. We have to sometimes look at the exponent, sometimes look at the denominator, and other times we look at what's inside of parentheses like we saw so far. So let's handle two of these cases and see if we can make sense of them. So examples of the above. Yeah, so let's try to do the integral of e to the negative 7x dx. Probably not too hard. When we were working with exponentials and derivatives, I often said just throw parentheses in the exponent because extra parentheses always help you out. And now that they're in the exponent, you kind of have a better idea of what the inside and the outside is. So let's work with that and say u equals negative 7x. And then we can handle this by implicit differentiation and say that du equals negative 7 dx. But I don't have negative 7 dx with this problem. So how do I reconcile this? Well, we do the same thing I just did above. That's kind of why I introduced it. So this equation du equals negative 7 dx is exactly equivalent to me saying negative 1/7 du equals dx. And so now when I work with my e's, it's really not too bad. I write it as e to the minus 7x dx, and as always, I split them up. And here, that piece is going to be u, and this piece is negative 1/7 du. So that gives me integral e to the u times negative 1/7 du, also known as negative 1/7 integral e to the u du. And we know how to integrate e to the u. It's one of our favorites. It just becomes itself plus c, and always substitute u back in. So this is negative 1/7 e to the negative 7x plus c. So that's not too bad. Let's handle one more e problem. Maybe do a little bit trickier one. This is the integral of e to the x squared plus 2x. And now I'm going to multiply this whole piece by x plus 1 dx. Yeah, and so now I have an exponential and I have a parentheses, and you're looking at me like, well, you said that u should be what's in parentheses usually, and I've also said that u should be what's in the exponent, and we need to kind of figure out priority here. So I'm going to give you a little cheat code here, and this is priorities for u. Priorities for choosing u. This is a super big cheat code here. So number 1, and we haven't seen this yet, it's denominator of power 1, of overall power 1. And what I mean by that is that this is going to basically be, this will be a log problem, a natural log problem. And we haven't seen any of those yet, but that's really priority number 1. Priority number 2 is going to be the piece in the exponent. And finally, priority number 3 is whatever's in parentheses. And what I mean by this is that when I say whatever is in parentheses, I mean that the other two don't exist, right? If a denominator of overall power 1 doesn't exist, then you skip it. If no exponentials, really what I mean by that is E problem. This will be an E problem. So if denominators of overall power 1 don't exist and an E doesn't exist, then you just do the parentheses, which is what we saw earlier. But in this case, an E exists. And that's what I mean by saying that we're going to do the priorities, and we're going to say that U should actually be the piece in the exponent. So hence U should be the piece in the exponent. So here for our problem, integral e to the x squared plus 2x times x plus 1 dx. I have parentheses, but that's priority number 3, and priority number 2 is the piece in the exponent. So we're actually going to let u be the piece in the exponent, which is x squared plus 2x. And that lets us calculate du, still by implicit differentiation, gives us 2x plus 2 dx. And 2x plus 2 dx, right, I'll put that in parentheses. Once again, that is not showing up in our problem, but it's something similar showing up in our problem. That's what I want you to keep thinking about every time you see these and you don't get du in your problem. You're saying, okay, can I at least multiply or divide this by something and get du? And the answer here is yes. In our problem, we have an x plus 1 here, right? And here this is 2x plus 2. Is there any multiple of x plus 1 that gives us 2x plus 2? Of course there is. It's 2. So really, this is saying, this is du over 2 equals x plus 1 dx. And all of a sudden, the world makes sense. Even in these coronavirus times, the world still makes sense. Okay, so this is going to make our life a lot easier. Because now I have everything I want. This becomes, I'll rewrite it out one more time, e to the x squared plus 2x times x plus 1 dx, and I have u, and I have really 1/2 du. And so what do I get? I get the integral e to the u times 1/2 du, and this can be rephrased as 1/2 integral e to the u du, and e's are our favorite integrals to take because they stay the same. And we just want to substitute u back in. So we decided that u was x squared plus 2x. And so this becomes 1/2 e to the x squared plus 2x plus c. So I've solved one more E problem for you, and I know this is feeling like a lot, but hopefully I'm writing it down relatively well. We have to handle one log problem, at least one log problem, before I can let you go, because there's one on your homework. So we might as well handle it. Let's look at a good example of a log problem, maybe. Yeah. Tricky stuff over here. Tricky stuff. So, example of a log problem. We're going to do the integral of x cubed over x to the fourth plus 1 dx. Yeah. So if we go up to our priorities, this is a huge deal right here. So we don't want to forget this priorities box because this is a huge deal. Priorities box. Denominator of overall power 1. What do I mean by that? I said overall power 1, and now you guys are saying, but there's a power of 4 in the denominator. But really what I'm saying is that the whole denominator, if I were to put parentheses around the denominator, there are no powers there. So in reality, what I mean is that this can be written like x cubed over x to the fourth plus 1. I've just put parentheses in the denominator. And on the outside of those parentheses, there's really a power of 1. Because, like, consider, for example, if the parentheses, the denominator was like x plus 1 squared, the whole thing, x plus 1 squared, that would not be an overall power 1 because, like, you already have parentheses there and you already have a squared and blah, blah, blah. So this is what I mean by an overall power 1. Then u will be the denominator, right? You choose u, it's the denominator of overall power 1. That's what I should say here. U equals the denominator of overall power 1, first of all, or the piece in the exponent, or whatever's in parentheses. So in this case, u equals the denominator of overall power 1. So u equals x to the fourth plus 1. And that gives us du equals 4x cubed. And do we have an dx, I guess? Do we have 4x cubed? No, we don't. But what do we have instead? I can just divide both sides by 4. I get 1/4 du equals x cubed dx. And it's hiding in there, but really we do have x cubed dx. So I would rewrite this as x cubed. I would rewrite the x cubed over x to the fourth plus 1, I would rewrite that as 1 divided by x to the fourth plus 1 times x cubed dx, and then it makes perfect sense. This is u, this is 1/4 du, and so we get integral 1 over u du, and that's going to go to the natural log of the absolute value of u plus c, which is also known as the absolute, oh, I'm missing a 1/4 here. 1/4, 1/4, 1/4 natural log of what was u, x to the fourth plus 1 plus c. So that's how you would handle a log problem. Anyway, that's all I have for today. I think it was a bit longer of a lecture. I'll make sure to make tomorrow short so you guys can, you guys can average at these 50-minute days. I was nice the first 2 days, so, be nice to me as well. All right, have a good one. Hope you're hanging in there. See you tomorrow.